Thank you very much. It is, thank you, Cho, for the invitation. It is an honor and a pleasure to speak here in front of you. And let's see, it's not yet 3:30, but I'll okay. Yeah, so I want to tell you about the role of Vinberg pairs in the theory of Higgs bundles. So before talking about Higgs bundles, let me tell you what are Vinberg pairs. And so the setup is having a G, a semisimple complex Lie group with Lie algebra G, so group G. And then we take an automorphism of the group of order m, bigger than 0, theta. Right? So this theta determines, of course, an automorphism of the Lie algebra that I will also denote by theta. And this determines a set mod m grading of the Lie algebra G. Right? So that is, G is a direct sum of GIs where the GIs are defined having as the eigenspaces in the Lie algebra for the action of theta with eigenvalue zeta to the I, where zeta is a primitive mth root of unity. Right? And so one has this bracket, Lie brackets of elements in GI with GJ are in GI plus J. So this is a set mod m grading defined by a finite order automorphism of order m. And so if mu m is the group of mth roots of unity, then clearly having a set mod m grading of the Lie algebra is equivalent to having a homomorphism from this group, mu m, into the group of automorphisms of the Lie algebra. That's very clear. And then we want to consider the subgroup of fixed points that I call G theta. And this group, G theta, this subgroup is a reductive group whose Lie algebra is G0, in the G0 in the grading. And so the fact that we have this commutator relation means that GI is stable under the action of G0, right? And so in fact, GI is stable under the adjoint action of the subgroup G theta. And I will call a Vinberg theta pair a pair consisting of this group G theta and the subspace GI, any subspace GI. So in the literature, these things are called theta groups or Vinberg theta representations. I like this other, also Vinberg pairs is a term that has been used. I prefer to specify theta here because there will be other Vinberg pairs that will appear in the story, right? And so sometimes we may replace the group of fixed points, G theta, by its connected component, or any group that is in between its connected component of the identity and the normalizer of G theta and G. The G sub i's are stable under the action of any of these subgroups, but most of the time we will be considering the group of fixed points. So the first example, that in a sense trivial but very important, of course, is the case where m is equal to 1 and then theta is just the identity. And of course, the only Vinberg pair that one has is just the pair consisting of the group and the Lie algebra with the adjoint action, right? A less trivial example is that of symmetric pairs, where m is 2, and then we have a set mod 2 grading of the Lie algebra, G0 plus G1. And this, the theory of symmetric pairs, is of course very important in the study of symmetric spaces and real forms of the group of the Lie algebra G and the group G. And let me just remind you about this connection with real forms. And so, first of all, to say that the real form of G is a subgroup, a real subgroup of G, which is the fixed point of an anti-holomorphic involution, sigma, that call a conjugation, right? And the relation between these objects and the theta being a holomorphic involution of the group is given by this result of Cartan, which says that given a holomorphic involution of G, one can always find a compact conjugation tau of G, that is a holomorphic, an anti-holomorphic involution that defines a compact real form, and that tau commutes with theta, and so I can consider sigma, and this defines another anti-holomorphic involution, and the real form that I am considering here. So you can think, when you want to think of real forms, either in terms of holomorphic involutions or anti-holomorphic involutions. And so here the equivalence here is by either conjugation by inner elements, inner automorphisms of G, or even also by outer automorphisms. I'll be interested in considering equivalence under the conjugation by inner automorphisms of G. Okay, so this is... Then another example that will appear in the story is that of cyclic quivers, right? And here M is bigger than 2, bigger or equal than 2. And so V is a complex vector space equipped with a set mod M grading, that is just a direct sum of subspaces Vi that are parameterized by Z mod M, right? So I have this vector space, and let me just say the group in this story is the special linear group of V, right? And the Lie algebra, the traceless endomorphisms. And the Z mod M grading is given by defining Gi as those traceless endomorphisms that bring Vj to Vj plus I for every j in Z mod M. And so in this situation, you can see that the group of fixed points, G theta, is the S of the product of the G of the general linear groups of the VIs, this meaning that the determinant of the product is 1. And G1 in particular is this hom from Vi to Vi plus 1, right? So, so we can represent that in a quiver, that we can define the quiver with M vertices indexed by Z mod M, and the arrows just go from I to I plus 1 for each I. And so this is really, then G1 is just the space of representations of this quiver, representations of type AN of this quiver, right? That can be represented into this diagram. If you have other classical groups, you can also have similar picture for the action of G theta on G1 interpreted in terms of some cyclic quiver with some extra structure. Yeah? Okay, so these are 3 examples, and I just want to emphasize here, in particular in relation to the lecture that Cho has given today about geometric invariant theory and Hitching vibration. We'll come to the Hitching vibration at some point. That Vinberg theory is concerned with the study of geometric invariant theory associated to the Vinberg theta pairs, the action of G theta on the GIs, and just recall the fundamental fact of the adjoint action of G on the Lie algebra, which is a Chevalier restriction theorem, that if you have T is a Cartan subalgebra and Wt is the Weil group, then the Chevalier restriction theorem tells us that there is an isomorphism between the GAT quotient for the action of G on its Lie algebra in terms of the action of the Weil group on T, right? So that's very well known, and that is the base, of course, of the Hitching map, actually, Hitching vibration, the original Hitching vibration. What am I saying? No, sorry, I'm going ahead of myself. Excuse me. Yeah, next case is precisely for the case of symmetric pairs. So that is when theta is an involution, right? And so here, so we have G is the sum of G0 plus G1. And this is the Cartan decomposition of the Lie algebra defined by the involution. And here one has the little Weil group of the pair defined by a maximal abelian subalgebra A of G1. And here, as Coston and Rallis exploited quite a lot, there is also a Chevalier restriction theorem establishing that the GIT quotient of the action of G theta on G1 is isomorphic to this maximal abeliance of algebra mod the little Weil group. Okay, so what actually rekindled my interest in Vinberg theta pairs, as I'm defining here, is this fact that I have been ignoring for many years, and it's only recently that I realized that there is, in fact, such a theorem and generalization of the two cases that I'm just telling you, and is a theorem that was proved by Vinberg a long time ago, as you can see, in 1976. The fact that there is actually a version of the Chevalier restriction theorem also in this situation. And so a key concept here is again that of a Cartan subspace that is a linear subspace A of G1, which is abelian as a Lie algebra, consisting entirely of semisimple elements and is maximal with respect to these properties, right? And so the little Weil group is defined like in the case of symmetric pairs, is just the normalizer of A in G theta and the quotient decentralizer. And this, he proves, is a finite linear group generated by semisimple transformations of A fixing a hyperplane. So hence, this invariant algebra is a polynomial ring. And the restriction of polynomial functions on G1 to A induces an isomorphism of invariant polynomial rings, or equivalently, we have this. So exactly the generalization of the Chevalier restriction theorem. And so let me just emphasize the fact that WA is a finite linear group generated by complex reflections implies exactly that what I said, that this is really a polynomial algebra and is generated by R algebraically independent polynomials, F1 to Fr, where R actually is the dimension of the Cartan subspace, and this is an invariant of the problem. Any Cartan subspace has the same dimension. It's conjugate under G theta. And so these degrees, so these are polynomials of certain degrees, and these are determined by the grading. So these are invariants of the problem. And the dimension of A is what we call the rank of the Vinberg pair, right? By the way, I didn't mention it, I think, or maybe I wrote it, but I defined Vinberg pairs as any pair with GI, but you can always reduce the study of these objects to the case of G1. You can always cook up a subalgebra of which your GI is the G1, right? A subalgebra of G. So it's just enough to study the case of G1. So something important that is also relevant later on in the study of Hitching vibrations and is the existence of a section in the case of the adjoint action of G into the Lie algebra. This is the constant section that one knows is very important. In the case of symmetric pairs, constant Rallis proved that there is indeed a section as well. Right? So this plays a role in the study of the Hitching vibration for symmetric pairs. And the existence of a similar section in this situation took actually quite a long time to be proved. This was conjectured by Popov, but only, I mean, some cases were proved some gradually, but it's only relatively recently that actually one has a proof of this section by these people. And in this context, sometimes it's referred as constant Weierstrass section. All right, so I will come back to this aspects when I mentioned the Hitching vibration. There are many interesting applications of Vinberg pairs. I just mentioned here a few. Of course, they are interesting from the point of view of representation theory. A very nice application of Vinberg and Elashvili immediately after introducing these objects was to the classification of trivectors in a nine-dimensional space. You see them appearing in the arithmetic theory of elliptic curves and Jacobians, and also very nice descriptions, explicit descriptions of the moduli spaces of vector bundles on curves of a small genus, or actually in relation to the moduli space of genus 2 curves. So they play a role, and even appearing in the context of physics, in string theory, in something called mysterious duality, and related to the Peso surfaces. So there's very many applications. But what I want to do today is to show you the a role that Vinberg theta pairs play in Higgs bundle theory. And some role, I mean, the role, I don't know, there are many aspects, there are many other things that may be relevant, but I want to mention some. And so then in doing that, I will review some old results. So I have been working for years on theta Vinberg pairs without realizing that they were theta Vinberg pairs. And so I'm revisiting from this more general context. And then I will mention some work, some work in progress in the study of the geometry of moduli spaces of cyclic Higgs bundles. These Higgs bundles are related to the Vinberg theta pairs, as I will explain. Interrupt me if there are questions, please. Do not hesitate. Yeah? Any question so far? Okay. So let's get into the theory of Higgs bundles. More generally, I will consider Higgs pairs in the following sense. So X is a compact Riemann surface of genus bigger than 2 with canonical line bundle, K. And then, just to explain this, this G will be actually in a minute, will be G theta. So I want to consider any G that is a reductive complex Lie group. And I have a representation of G in this vector space, GLV. All right, so these are the ingredients, the curve, the group, and the representation. And then I want to study what I will call GV Higgs pairs. These are pairs, Phi, consisting of a holomorphic principal G bundle, or E on X, and then the Higgs field, which is a section of the vector bundle that I'll denote by EV. I will use all the notation, this notation in brackets all the time for referring to an associated bundle to a representation, in this case to this representation rho, tensor by K. Here we could put any other line bundle, and in fact the different powers of K will make the appearance, a brief appearance in the story shortly. So there are suitable notions of stability and semi-stability, stability, polystability, all you need to construct a moduli space of polystable or semi-stable objects of this type that I will call MGV, so the moduli space of pairs of this type associated to this data. These are complex algebraic varieties, and in particular, of course, a prominent case is when rho is the adjoint representation into its Lie algebra, and this G now vector space is the Lie algebra. Higgs pairs are nothing but what we know as Higgs bundles, the Higgs bundles introduced by Hitching. Right? And for this special moduli of Higgs bundles, of pairs of this type, I will just use the simpler notation MG. So MG is the moduli space of polystable G Higgs bundles. Okay? So MG, there are people in this audience that know a lot about these moduli spaces. They're quasi-projective varieties with a great geometric structure. In particular, they are hyperkähler in the smooth locus. And some aspect that I want to emphasize here also is the relation of these objects, G Higgs bundles, to representations of the fundamental group of the curve, of the Riemann surface X, right? And so I introduce here the G character variety of the fundamental group as the GIT quotient of the space of homomorphisms of pi 1x into G, mod the quotient by conjugation by the group G. So it's a moduli space of representations or G character variety. And the relation between Higgs bundles is given by the famous non-abelian Hodge correspondence that establishes, in particular, a homeomorphism between the character variety and the moduli space of G Higgs bundles. Yeah? So here I'm assuming that G is semisimple. There are versions of this for a reductive group, but I will be today devoted to the case in which I consider Higgs bundles for a semisimple G. In fact, from now on, G will be semisimple all the time. And so then let's consider theta an automorphism of the group of order M. And recall, we have this set mod M grading of the Lie algebra. And we have our Vinberg pairs, so the group fixed point subgroup acting on GI. And I want to do this construction of Higgs pairs to this particular pairs. So I want to consider the moduli space of G theta GI Higgs pairs, right? In the sense that I defined previously, the moduli space of G theta GI Higgs pairs over X, right? So the thing is that this moduli spaces, which of Higgs pairs of this kind, do appear naturally inside the moduli space of G Higgs bundles, and I'll explain how that is. And they do appear, in fact, as fixed points under the action of a cyclic group. This was systematically studied jointly in a paper with Riemann. And so to explain that, let me just tell you how the group of automorphisms of the group G acts on the moduli space in the following way. If I have an automorphism of G and I have a G Higgs bundle, then I have another G Higgs bundle in which the principal G bundle is just associated to this automorphism. So this is what I call alpha E. And there is a similar action on the Higgs field. So I have this action of the group of automorphisms. And because we are considering the moduli space, this action, actually the group of inner automorphisms is trivial. And so this action descends to the outer group, the quotient of the group of automorphisms by inner automorphisms. So I have this action. And then I have also an important action in the moduli space of the Higgs bundles by rescaling the Higgs field, an action of C star, scalars, just multiplying the Higgs field phi by a certain number in C star lambda, let's say. Okay? So now, if I consider the group mu M of the M roots of unity, and in particular zeta is a primitive M's root of unity, I defined a homomorphism from this cyclic group. I'm going to inject this group in here in a very simple way. I associate to zeta the automorphism of order M theta and zeta itself here, right? And so I'll call gamma the image. So of course the image is just isomorphic to mu M, the group of M roots of unity. And so I am considering the action of gamma on the moduli space by combining, well, precisely given by these actions, which is combining the action of theta on the bundle and the Higgs field and multiplying the Higgs field by this primitive root of unity. Okay, so that is an action of gamma on the moduli space. And so the fact is that if I consider the moduli space of pairs G theta G1, I claim there is a map from this moduli space into the moduli space of G Higgs bundles that is defined by extending the structure group of G theta. So the bundle is a G theta bundle. I extend it to G, so I have a G bundle. And here the Higgs field is in G1, but G1 is a subspace of G of the Lie algebra, so I extend that by 0 to the other terms. So there is, and what is not trivial is that polystable objects here do map to polystable objects. One proves that. And so we have this finite map here. And so if I consider the image of that map, which I call M tilde, then the fact is, that is easy to prove, actually, is that that image is in the fixed point subvariety under the action of gamma that I defined previously. So these are fixed points under that action. But in fact, because the action of theta, which remember was an automorphism of order m, only depends on the class in the outer group, right? There are other fixed points, other subvarieties, and this can be described as follows. If consider the automorphisms of order m in the group of automorphism of G, so the set of elements of order m, and here I consider so this is the image in the outer group of this, and here I'm considering this equivalence is the one that I told you before, by inner, conjugation by inner automorphisms. So there is this map that we call the clique map, and for an element here, the pre-image in here, a bunch of classes here, is what we call the clique, defined by A. And this set here can be described very explicitly, and one can show that this is actually can be described in terms of non-abelian Galois cohomology as an H1 of set M, the adjoint group, where set M acts, of course, here by theta, right? So you have this, so this is the pre-image, and the statement is that if you consider the smooth locus of points, G-Higgs bundles that are stable and simple, so the only automorphisms are given by the center of the group, so that's the smooth locus, and you consider the action only on the smooth locus, that is contained here. So that is contained in the union of all these subvarieties associated to Vinberg pairs and different Vinberg pairs. These Vinberg pairs are really defined by different classes in this non-abelian cohomology, right? And so the image of these moduli spaces of G theta G1 in the moduli space Higgs bundles we call cyclic G-Higgs bundles, and we call them cyclic G-Higgs bundles because they are fixed points under the action of the cyclic group, right? And these cyclic G-Higgs bundles do play an important role in a number of problems related to minimal surfaces, or you know, in various aspects of the geometry of Higgs bundles that I cannot enter into it, but there are many authors that have been in relation to total lattices and things like this. So there's some important subvarieties of the moduli space of the Higgs bundles. And if you wonder what happens to the other fellows, to the GIs, you know, if we, instead of having G1, I have GI, they also do appear as fixed points, but now for a different action of the cyclic group, and where you actually multiply the Higgs field by a power of the primitive root. Okay, we will focus on these ones here today. So so set M gradings, you know, appear in the literature in the context of Higgs bundles, but in particular, set mod 2 gradings had been studied very extensively for a long time, and in the study of Higgs bundles, for the simple reason that they do also have an interpretation. These cyclic Higgs bundles have an interpretations in terms of character varieties, right? And so in this situation, so if M is equal to 2, right, and so theta defines a set 2 grading, G0 plus G1, the fact is that, as I mentioned before, associated to theta, there is an anti-holomorphic involution and a real form, G sigma, as I explained before, thanks to Cartan. And so you can define the character variety for this G sigma in a similar way as we did before for G. And there is also, in this situation, a non-abelian Hodge correspondence that establishes a homeomorphism between the moduli space of G theta G1 Higgs pairs and the character variety for this real form. And this homeomorphism, as in the case of G, but more especially in the case of real groups, has been essential to study character varieties for real forms, and in particular for some special real forms, and is a central ingredient in what is called higher Teichmüller theory. I will mention some of that in passing. Okay. Okay. So in particular, in this particular situation, this cyclic Higgs bundles are fixed points under the action of theta, as before, and now it's just multiplication by -1 on the Higgs field. So, and they also play an important role, these subvarieties, in the context of the Langlands duality and mirror symmetry between modular spaces of Higgs bundles for G and Langlands dual, and this defined important Lagrangian subvarieties of Mg. Okay, so I have explained set mod M gradings, but I want to talk now about other kind of gradings. I want to talk about set gradings. And I will establish a relation between the two in a minute. So again, G is a semisimple complex Lie group. And here, the killing form, B, will play a role. So I'm explaining some ingredients of a theory that we have developed recently in collaboration with Olivier Bicard, Brian Collier, and Domingo Toledo. And this is the following, but let me explain to you what is the context. So a set grading is very similar to what I said before, is now a decomposition of G in GIs, but the i's are parameterized by the integers and satisfy the usual relation of a grading. And in this setup, there is always an element in G0, which we call the grading element, zeta, that defines the GIs precisely as the eigenspaces for the adjoint action of zeta on the Lie algebra, right? So it's this I is this I. Okay, so having a set grading is equivalent to having a homomorphism from C star to the group of automorphisms of G. And so Vinberg, again, in fact, a year before the introduction of the other pairs and his theory of geometric invariant, his GIT theory that I explained before, he introduced these pairs, and here is an important result, that if you take out I equal to 0, all these GIs are pre-homogeneous vector spaces for the action of G0. So what this means is that in all GIs, there is a unique open dense G0 orbit. So this open dense orbit is a homogeneous space, is G0 mod some isotropic subgroup. Yeah? Okay, so we call these pairs of G0 GI Vinberg C star pairs. And you'll understand why this is not a standard in the literature. We have introduced that notation in order to distinguish the two kinds of pairs, but you'll understand why we consider that. So again, if you have a set grading, you can consider Higgs pairs associated to this new Vinberg C star pairs, right? Where you have this is a G0 bundle and a Higgs field taking its values in GI, in the associated vector bundle. And again, by extension of the structure group, you can define a G Higgs bundle associated to such a pair. So that is a principal G bundle and a section of the adjoint bundle, tensor the canonical. And so then the thing, these objects, so a G Higgs bundle that is obtained in this way, or in other words, that can be reduced to a pair of this kind, is called a Hodge bundle. And the crucial result by Simpson is that remember there was an action of CS star in the moduli space of Higgs bundles by multiplying the Higgs field. And the fixed points under this action are always Hodge bundles for some Z grading. So these objects are the objects that described the fixed points in the moduli space under the action of CS star in the moduli space of G Higgs bundles, and they are in the global nilpotent cont, and they are responsible for, in some sense, for the topology of the moduli space, and that has been exploited by a number of authors. So, this, via the non-abelian Hodge correspondence, these objects correspond to holonomies of complex variations of Hodge's structure, right? That's something I won't be emphasizing today here. All right. So, again, we can devote our attention to Vinberg CS star pair with G1, because we can always reduce the study of the others to G1. And consider omega to be the open orbit that, remember, there was an open dense orbit under the action of G0. And so here's the machinery that we have developed in this work that I mentioned with Olivier Vicard, Brian Collier, and Domingo Toledo, that paper that appeared recently. And so we defined Toledo character of G0 as follows, just basically pairing with using the killing form. There is a normalizing factor that we can forget today. It's not essential. So we have a character of G0, the G0 appearing in the grading. And so then, using this, we can define now the notion of rank for any element that is in G1. A notion of rank that in many examples is actually the rank of some homomorphism, but in general is a wild animal. And the way to do that, a way to do that is to complete. So here is an element E in G1. This in this CS star pairs, all these elements, all the GIs are consist entirely of nilpotent elements. So in particular, in G1, all the elements in G1 are nilpotent. The GIT invariant, the GIT quotient theory of these pre-homogeneous vector spaces is uninteresting because they all go to to this one point. And so you complete this nilpotent element to an SL2 triple, where you can take F in the G-1 and H is in G0, and we define the Toledo rank of E by using this character and applying to H. And that allows us to define the Toledo rank of the pair, of this Vinberg pair, by considering the rank of any element in the open orbit. I'll give some examples. You understand what is this, some instances where you have a feeling this is really a rank, and so on. So now, if we have a G0, G1 Higgs pair, and consider the Toledo character associated to this that we just defined. Now, okay, if this character lives to the group, wonderful. But if not, you can multiply it by some rational number sufficiently large, right, or integer sufficiently large, in a way that it lifts to a character of the group G0. And so using this character and the fact that this is a G0 bundle, you obtain a line bundle. This line bundle is what I denote, well, I don't denote it in any way, but I refer here the degree of that line bundle. And so we define the Toledo invariant of the pair as this number that is the degree of that line bundle divided by the Q that we use to lift the character from G0, the Lie algebra, to the group, okay? And so here is the main result, or a main result in our paper, that is what we call Arakelov-Milnor inequality, that is given a bound on this Toledo invariant in terms of the rank of phi, where by rank of phi we mean the rank of phi x for a generic element in the curve, right? And in particular, we obtain this inequality here in terms of the rank of the Vinberg pair, and G here is the genus of the curve. We call it Milnor because it generalizes a famous inequality by Milnor, and called Milnor-Wood inequality that I will mention in a minute. So in the context of symmetric spaces, right, and character varieties for real groups of Hermitian type, but also Arakelov because it does generalize also, or is similar to inequalities that appear in the literature for classical variations of Hodge's structure, and so that is why we put that fancy name. So, okay, so consider then a Z grading, and we have the grading element, remember, zeta, and G0 with the centralizer of zeta. I want to talk now how these Hodge bundles are related to the cyclic Higgs bundles that I explained before for set mod M gradings, right? These Hodge bundles are fixed points on the action of C star, right? But now we want to construct some, of course they are a fixed point under the action of any cyclic subgroup inside of C star, but we want to construct some examples of cyclic Higgs bundles that appear from this set grading. And so here's the thing. Consider, let M the smallest integer that appear in this set grading, for which all the GJs are 0, from absolute value of J bigger than M. So you just take the smallest integer of that type. So then we have this canonical set mod M grading defined that I call GI bar, right? With the GI bar, it's just taking the GI together with the GI minus M, that piece there. By the way, this is all very abstract, and I should just, a long time ago, should have given you a nice example to keep in mind. We'll see some, but let me actually an example related to this cyclic quivers, right? The example of, we have vector bundles. So this is right. Em minus 1, and then this is Pm minus 2, right? So these are fixed points in the moduli space of the Higgs bundles, right? I'm thinking now here in vector bundle terms, right? And so we do have this cyclic quiver that I mentioned before, Vm minus 1. So these objects, all these homomorphisms are twisted by k. So this go from E0 to 1 tensor k, etc. And you can embed this really in a G Higgs bundle for SL and C, right? Where E is the direct sum of all these vector bundles, right? I'm thinking now in vector bundle terms. I mean, an SL and C principal bundle and a holomorphic vector bundle with trivial determinant, same thing for me, right? And then you have this phi, right? That you can. I always get this wrong with this. Sort of. You can embed it. You just have 0, 0. So phi m minus 1, and then phi 0, 0, 0, and then you can go to 0, right? So phi m minus 2, 0. So this is the way, I mean, this is how you see this object inside the moduli space of SLNC Higgs bundles. And a Hodge bundle is, an example of Hodge bundle is when this thing is 0, right? And a cyclic Higgs bundle is when actually of order m is when you do have also this homomorphism here. So this is a nice example to keep in mind. And in fact, okay, I don't want to go ahead of myself. Let me just, yeah, right. So, so we want to study, I defined previously this G0, G1 Higgs pairs for set M gradings, but I want to do it for this particular set mod M gradings, right? And so the one interesting thing here is the following, is that now in this situation, right, when you consider this kind of Z mod M grading that I was describing, right? The G1 bar, recall, was G1 plus G1 minus M. And so a Higgs field here has two pieces, phi plus and phi minus. So where phi plus is in here and phi minus is in here, right? And okay, so an example of this is exactly this situation, right? So this is really, this is the phi plus, right? And then this here is the phi minus, right? And so the thing is that this Toledo invariant that I'm just want to convey the fact that this Toledo invariant and this bound that we found can be extended to this cyclic Higgs bundles. That is, here you have a the Toledo invariant for the G0, G1 here, so I call it tau plus, using the Toledo character of this pair, right? And as we saw before, if phi minus is 0, then one has this Arakelov-Miller inequality. But what is actually interesting is that that inequality is a stronger result, and is that that inequality can be extended even if phi minus is different than 0. And so if this is semi-stable, then we still have this inequality. This is proved with my student Miguel Gonzalez. And we can also, consider the Toledo invariant of the other piece of phi minus, and using the Toledo character for this other pair, for this other CS star Vinberg pair, right? And noticing that the grading element for this thing is not the same as before. The grading element is actually modified in this way, right? And if phi plus is 0, then we have the Arakelov-Miller inequality, but in general, we cannot guarantee the inequality if you have that phi plus is different than 0. However, this happens sometimes under some conditions, and one such condition is precisely when m is equal to 2. And so in this case, the set grading is of the form G minus 1 plus G0 plus G1. And then the associated set 2 grading that we have via the construction before is that G0 bar is G0 and G1 bar is G1 plus G minus 1. And this is exactly the situation that corresponds to real forms of Hermitian type. Yeah? So whenever you have a set grading of a complex simple algebra of this kind, of semisimple, then this corresponds, the set 2 grading corresponds to a real form of Hermitian type. And is exactly in this situation where one has that this inequality that goes in the two directions, because in this situation, the tau plus and the tau minus that I defined, one is the opposite of the other. And we have this, we recover by this theorem the Milnor-Wood inequality that one has in this context. So this, if G is simple, then this corresponds to real forms of Hermitian type, and this is is a real form. If it's a classical real Lie algebra, is of this form: SUPQ, SP2NR, SO star to N. So these are the famous, the important classification of Lie algebras that lead to real forms of Hermitian type, meaning that actually the quotient of the real form by the maximal compact is a Hermitian symmetric space of the non-compact type. Yeah? And in this context, the inequality that we proved, this inequality here, in terms, in the language of Higgs bundles, recovers. Is actually the Milnor-Wood inequality for the Toledo invariant that was introduced by Toledo in the mid-80s, and that has been was proved by Milnor. In fact, when for SL2R, where R is equal to 1, right? And and so and whose proof in general been given by Burger, Jossi, and Wienhardt. So I shouldn't be drinking this. One thing special about this maximal, when the Toledo invariant is maximal, that happens in the Hermitian case that I just described, is a rigidity result that is of great importance. And this rigidity result manifests in various ways, right? And but is ultimately responsible for giving a parametrization, a construction of these higher Teichmüller spaces that are appearing in the field of higher Teichmüller theory, and that consist entirely of representations that are of the fundamental group that are discrete and faithful, and in fact, going back to the case of Milnor, where this is just the Euler class of a SL2R flat bundle. So Milnor actually, so this maximal situation that we're describing corresponds precisely to the component consisting of Fuchsian representations, and is a component that can be identified with the Teichmüller space of the surface. So this is exactly this theory that we are mentioning here corresponds to the generalization of this Teichmüller space, and these parametrizations that we call Cayley correspondence is actually in the case of SL2R is the parametrization of Teichmüller space in terms of quadratic differentials, holomorphic differentials that Hitching gives in his first paper, right? Okay, so in fact, well, this was the story about these groups of Hermitian type, but all this that I have been trying to explain is a generalization of this Toledo invariant and all these inequalities and this rigidity in a much larger context, in the context of Hodge bundles and in the context of these cyclic Higgs bundles. All right, so I want to move to something else. I want to, in fact, as I said before, what made me very interested again in this Vinberg theta pairs, that is the role that they play in relation to the Hitching vibration. Right? I ended up, while I was trying to investigate that, I ended up realizing that there were these other aspects related to the Toledo invariant and to these bounds that are relevant in studying these subvarieties of cyclic Higgs bundles, right? And not paying all the attention to this Hitching map, but this is and a remedy. And what really motivated this work was in trying to find more examples of what Châu has been telling us today, of the generalizations of the Hitching vibration. And in particular, give examples of the, with more or less difficulty, of the regular quotient that you have been explaining today, right? And so let me just, so behind the screen there is a lot of stuff about Hitching vibrations that Châu was telling us. Let me just take a more down-to-earth approach to the definition of the Hitching map. And so again, consider theta an automorphism of order m, and we have a set modem grading defined as this, and we have this Vinberg theta pairs and the moduli space of this Higgs pairs associated to the Vinberg theta pairs. And the basic crucial fact that was proved by Vinberg in this generality is the Chevalley restriction theorem, and the fact that this algebra is free algebra generated by these polynomials. I mean, we have a basis of polynomials f1 to fr, where r was the dimension of this Cartan subspace, and what we call the rank of this pair. And the di's are the degrees of these polynomials. And let me just define the Hitching map as directly from the moduli space of these pairs by evaluating these polynomials on the Higgs field. And so by evaluating these polynomials on the Higgs field, we have precisely a map. My notation for the Hitching base is B of g theta g1. And this is the sum of holomorphic sections of these powers of the canonical, where these di's are the degrees of the polynomials. And of course, the basic example, the example defined initially by Hitching, corresponds to m equals 1, and r is nothing but the rank of G, and this d1 to dr are the exponents of the group G, as we know. And so just to remind you, so Hitching gave a spectral curve description of the generic fibers of this for the classical groups, and Boville, Narasimhan Raman studied this, and so Donaghy and Gates-Curry gave a cameral curve description for general G as a gerb, in the sense that Châu has been explaining before, showing that, you know, with generic abelian fibers, and the Donaghy-Gates-Curry approach was reformulated by Ngo in his proof of the fundamental lemma, as everyone here knows. And again, in connection to character varieties, a section of this map based on the constant section, a section of this map, of the Hitching map defined by Hitching, provided another, perhaps, I mean, actually the first example of, we can call these higher Teichmüller spaces. So a component of the moduli space of the character variety for split real forms, and consisting entirely of discrete and faithful representations. The situation that I was telling you before, the Hermitian case, provides other instances with maximal Toledo invariant, are other instances of these higher Teichmüller spaces. So the case m equals 2 that Châu mentioned in his talk, in reference in particular to U and N, the group real form U and N, is the case of symmetric pairs. And here the situation is more involved. And so Shaposnik studied gave a spectral curve approach for classical real forms, and my former student Peon Nieto in her thesis gave a cameral curve approach for arbitrary real forms. But from either point of view, it was clear that in general, the fibers are not abelian, and in fact, they are abelian if the real form is quasi-split. For example, the case of UNN or UNN plus 1, or the split real forms, right, are examples of quasi-split real forms. And so following the approach of Donaghy, Gates-Curry, and Go, Anna Peon and myself gave a GERF description of this vibration, where we realized that one had to consider some other quotient, the regular quotient, but we didn't give any explicit description of that, right? We just realized that you cannot descend to the usual GIT quotient. you need this other animal, right? And this has been pursued very nicely in the recent work in progress, almost finished, I think, by Thomas Meister and Benedict Morrissey. And the aspect linking to the fundamental lemma, also studied by Spencer Leslie in this situation of symmetric pairs. And also in this situation, building on the Costan-Rallis section that exists in that I mentioned before, we can construct with Ramanan and Anna, we construct a section of the Hitching vibration for this symmetric pair situation. So the general case of Vinberg theta pairs here is for which I have really mostly questions, right? But we are making, with my student Miguel Gonzalez, making progress. And one thing, for example, is about when is it that you have a billion fibers? And the situation of having a billion fibers is, if you take the symmetric pair case, one possible definition of what we could call quasi-split in this context would be that the centralizer in G0 of this Cartan subspace that Vinberg constructed be a billion. So that is, for example, in this case, yeah, this actually is a nice example. In this example, that corresponds to the ranks of all these vector bundles being equal or different by 1. For example, notice that actually the case that where m is equal to 2 here, which is this example, this quiver corresponds to the group that SUNN that was described before by Chow, and so the SUNN corresponds to having ranks equal. That's the quasi-split case. Also SUNN plus 1 is quasi-split, and in general, for this particular quivers, as I said, all the ranks equal or different by 1. And in the case of all ranks equal, my student Miguel is giving a spectral curve description similar to the one given by Shaposnik. But I think it would be very interesting to study the regular quotient in this particular situation. And we have learned from the symmetric pair case that is not that easy. So obviously here there will be some work to be done. So it's a good example, I think, for those attending the course, right, and to try to develop maybe in the next few weeks. Another thing that is still not resolved here in this generality is about the existence of a section of the Hitching map for this general situation, building on this, Costron-Ballestras section. So that is another open question that is in this problem. And of course, there might be, relative theta versions of the fundamental lemma, but that's not my job. So my job is over now. Thank you.